Hello, everyone. Welcome to the PARI Center and our new series, The Science of Wholeness, Perspectives from Physics, Ecology, Psychology, and Philosophy. Over 3 weekends, we will investigate the extent to which modern science has encountered aspects of wholeness, non-local consciousness, and the subject-object distinction. We will also consider what a post-reductionist science might look like, drawing on the experiences of indigenous cultures. Today we will be discussing, does quantum theory reveal an underlying wholeness to reality? We'd like to thank the curator and chair for this series, Dr. Jonathan Allday, who has thoughtfully put together this series in the most beautiful way. Jonathan Allday has a PhD in elementary particle physics. He has worked as a physics teacher for 30 years in a variety of independent day and boarding schools in the UK. He retired in 2020 and now runs a consulting company providing training and educational advice for schools. Jonathan wrote his first book, Quarks, Leptons, and the Big Bang, which was published in 1998 and is about to enter its 4th edition. Jonathan has also collaborated on several textbooks and written his own books on quantum theory, general relativity, and the Apollo moon missions. I will now hand over the discussion to Jonathan.
Evening, everybody, and thank you very much indeed for that great intro, as always. I'm going to just bear with me a second. I'm going to just share my screen, and then I'm going to kick off the presentation. Hopefully, then everybody can see that. Is that everyone see that? Okay. If you don't mind, I'm just going to switch my video off while I'm actually doing the presentation, because my Wi-Fi at home just occasionally glitches out a bit on me, and I'm just trying to make sure that I maintain that you can see the pictures, which are far more important than seeing my face. So this is going to be a talk of 2 halves, perhaps not equal halves in terms of duration. But what I want to do in the first part is just to, for some of you, a slight recap. If you've seen a couple of my talks in the past, I want to do a little bit of a quantum theory primer. I'm going to explore a few more aspects of quantum theory than I've talked about before. That's going to be the first half. And then the second half is going to be to go back and look at, well, I've picked out these particularly influential and important books here, and just look again at them where we are now, better part of 50 years on, and just see what they had to say in their day, whether it actually holds up to detailed scrutiny, or whether we actually possibly need to be a little bit more nuanced about our conclusions. And a little bit of a spoiler there, I'm going to suggest that these well-meaning and certainly highly influential books, they were very influential on me as a young physicist, about age 13 or 14 when I read them. I think they possibly overpitched in retrospect what they were trying to do slightly, but that's possibly slightly contentious for some of you, and I'd obviously welcome discussion about that a bit later. Now, when I was sort of looking around on the internet for matters quantum related, I came across a few websites, and this particular one, although the pictures dotted across the screen here are from more than one website, and there's more than one quote going on here, but I've got a sort of terminology which I've pinched. I think I pinched it from John Polkinghorne, you always steal from the best, about quantum hype. And I think the quote that I've got there, which is directly off a nameless website, is a classic example of what I refer to as quantum hype. Our quantum loop works within the quantum field of unlimited potentials and possibilities to produce a whole host of enhanced life force energy effects and benefits for you. These benefits include the possibilities of bringing some relief to annoying aches and pains. First time I've seen quantum theory used to relieve aches and pains. Normally it generates headaches and other pains. Greatly enhanced dreaming and visions, much easier and smoother emotional release. A few people, students I know, who would be a little bit surprised that quantum theory brings emotional release. Energetic balancing and a swifter relaxation. Really? into much deeper and more expansive meditations, greatly improved sleep, and an easy way to quickly charge your drinking water. And I'm going to move on. Okay, right. So there's the idea, which we're going to investigate, to how much this sort of quantum hype is actually justifiable or justified. And as I said, I'd like to take a little bit of time initially to try and do a little bit of a quantum primer, discuss some aspects of quantum theory and what the mathematics, in a sense, is trying to do for us. Although, don't worry, I'm not going to be getting you to do any sort of calculations. Now, one of the basic ideas of quantum theory is what we refer to as the quantum state. And quantum states really tell us the sum total of all the information we could possibly know about a particular system. So we might have a quantum state of an electron, quantum state of an atom, a molecule, quantum state of a measuring device. In each case, the quantum state is expressing for us the total amount of information that is accessible about that system in those circumstances. Quantum theory breaks that state down into a collection of amplitudes. Now, you're going to see these funny angular bracket symbols popping up all over the place. They're just a way of writing down that we are referring to a particular state. So what I've put up on the screen on the top right there is, on the left-hand side, you've got that angular bracket around the Greek letter psi, and that's saying we have a state, which I'm calling psi. And on the other side, I'm saying it is composed of two other states, a state which I'm calling state 1 and a state which I'm calling state 2. And the numbers in front of those states, A1, A2, are what is known in the trade as the amplitudes. And the amplitude is really where the physics lies. So we've got our initial state on one side of our balance there, and we've got the two possible final states on the other side, and these are the amplitudes, which are expressing for us how likely it is under certain circumstance that the psi state will collapse into, bit of a spoiler there, either state 1 or state 2. Now, there's plenty of equations, Schrödinger's equation being the obvious one. Heisenberg's got a version as well, which help us calculate what these amplitudes are in different situations. And again, it's the amplitude that the physicists want to calculate, because that's telling us what's going on, or it's telling us the tendencies for what are going on. Now, sometimes, rather than it being a choice between one state and another, the particular outcomes might be continuous, by which I mean there's lots and lots and lots of possibilities all crowded up against each other so that they form a continuous span of possibilities. Something like the position of the electron or the atom would be a continuous span. The momentum would be a continuous span. In which case, rather than having a discrete set of numbers like A1, A2, etc., my amplitude actually becomes also a continuous spread of numbers, what we call in the trade an amplitude function. You can see I've highlighted that possibility in that other equation on the right there. In this case, we're writing the amplitude as a function, a spread of numbers that depend on position and depend on time. In other words, you give me a position, you give me a time, and I will calculate the value of psi at that position at that time. And that will be the amplitude at that position at that time. So this is, as I said, a spread, what we call a function, rather than a collection of individual numbers like A1 and A2 there. And sometimes it's what's called the wave function. Now, if you've come across quantum theory at some point in the past, chances are you've heard somebody like me or read somebody like me yabbering on about the wave function. I tend to talk in terms of amplitudes, but in some ways, they're very, very much an interchangeable idea. Maybe we talk about amplitudes if it's just a small set of possibilities like A1 and A2. Maybe we talk about a wave function if it's a continuous spread. but really and truly, we are talking about the same kind of thing. Now, one very important rule, which was developed by the physicist called Max Born, and we now know as the Born rule, is it tells us how we turn these amplitudes into something that we can actually, in a sense, compare to experiment. Because the amplitude doesn't tell us whether the initial state is going to definitely turn into state 1 or definitely turn into state 2. The physics doesn't allow us to do that. Quantum theory does not allow us to do that. What it does allow us to do is calculate the probability that that size state will turn into 1, or the probability that it'll turn into 2. And those probabilities are determined by the relevant amplitudes. And it was a big step forward in quantum theory because we had these wave functions, we had the Schrödinger equation, we could calculate the amplitudes, but it was the big step forward that Born made, which showed us how those amplitudes related to probabilities. And what Born said is you get the probability of an outcome by taking the complex square of the amplitude. Now, if your mathematics, you didn't get the chance to do mathematics sufficiently to quite understand what I mean by the complex square of an amplitude, then just simply think of it as being, we take the amplitude and square it, i.e. 2 times 2 is 4, squaring 2. It's a little bit more in depth than that because, as I've argued in a previous talk, these amplitudes are what are called complex numbers, and so we need to multiply the complex number by its complex conjugate. But really and truly, that doesn't directly impinge on any physics I'm going to talk about today. So if you're not happy about that, then just think of it as squaring it. So in other words, what I'm trying to say is this, that if we want to know the probability that my size state will turn into state 1, we take that number, that amplitude A1, and we square it. And that will tell us the probability. The probability that psi will turn into state 2 will be A2 squared. And if we've done our calculations properly, and we've normalized it in the technical jargon, and the only 2 possibilities are 1 and 2, then those probabilities, that A1 squared plus A2 squared, must add up to 100%, or a probability of 1, if you like. Now, the important thing about these probabilities are that they're going to be what I refer to as a quantum probability. In other words, it's a fundamental probability. It is, in some sense, expressing an absolute randomness in nature. I'll talk a little bit more about that in a few minutes' time. But the important point is this. It's not saying we have to calculate a probability because we don't understand the physics enough to calculate exactly. It's because there is no physics that enables us to calculate exactly. Not even the electron knows where it's going to be until it discovers itself there when you make a measurement. And oh, by the way, seeing as I've brought up position, then I should also point out, as I have there, if you want to calculate the probability of finding my electron in a kind of small interval of distance, somewhere between x and x plus delta x, then we square the amplitude, we square our wave function, we complex square it, just as I did those individual numbers. Now, notice also, this is an assumed rule. This is an assumption that we add on to quantum theory. Otherwise, we can't relate our amplitudes to what we actually find when we do our experiments. Although it has to be said that if you're an adherent to the many worlds view, then certainly people like David Deutsch claim to have actually proven the Born rule based on the assumptions of the many worlds interpretation. You may have noticed that my voice went slightly up when I said that, possibly a little more than I intended. It's not a proof that I personally buy into. In any case, the Born rule is well checked by experiment, and so we are confident that this is an aspect of quantum theory which very much helps us relate our calculations to what we find in experiments. Now, the entire way in which we've had this state set up is kind of based on the notion that we have this initial state, some measurement will happen, in which case we will find either the particular physical property we're measuring will have value number 1 or value 2 or value 3 or value 4, etc. And as a result of that measurement, the state will change into state 1. State 1 being the state of the system when it has value 1 of the property. Or state 3 is the state of the system when it has value 3 of the property. An interesting point to be pondering, of course, is what is the value of the property before we take the measurement? So if we do have some property that could have 5 possible values, then what value does it have in the initial state? Does it have a value in the initial state, or does the property actually manifest a value when the measurement actually happens? In this particular case, because I've happened to have come up with 5 different options for the results of the measurement, I would write my initial state in that fashion. So you can see we've now got 4 amplitudes, A1 through to, 5 amplitudes, A1 through to A5. And what we're saying, therefore, is the probability that I will find as a result of my measurement, value 1 will be A1 squared. The probability that my measurement will come up with value 2 is A2 squared. The probability that it'll come up with value 5 is A5 squared, yada, yada, yada. Now, because of that basic way in which it's set up, that we are describing the state in terms of what possibilities it might turn into, then quantum theory is often expressed or often described as saying that quantum theory itself describes systems in terms of what they might become rather than what they actually are. Nice quote there from Henry Stapp, that the elementary particle is, in essence, a set of relationships that reaches outwards to other things. Because the state is, after all, a collection of amplitudes which describe transitions or possible changes into other states. So this may well be an important clue, that maybe what we should be thinking about as the fundamental aspects of reality, at least as far as quantum theory is concerned, is processes, not things. Now, personally, I happen to think this is a very fruitful way of pursuing things. Now, it is also fair to say that states will evolve over time. These amplitudes do not stay completely fixed for all time. They will change over time. In fact, you saw earlier on, I wrote psi or as a function of x and t, position and time, which kind of brought up the idea already that these amplitudes can and will change over time. And it's important to appreciate that that process, the process by which the amplitudes evolve over time, is completely deterministic. There is no randomness, there is no unpredictability at work here. If you tell me the amplitude at a particular time and you explain to me the physics that's going on in the system, then I can calculate what the amplitude will be at any point in the future at any place. I mean, in essence, it's governed by equations like the Schrödinger equation, and you can see my amplitude psi is sitting in there. Now, again, this may be pretty indigestible differential equation for a lot of you, and I certainly don't intend to talk about it in any great detail. I'd just like to point out to you that this bit on that side kind of represents the kinetic energy of the system. This bit represents the potential energy, what's going on inside the system, and that bit represents the total amount of energy that the system has, which is clearly the sum of the kinetic and the potential energies. But really what I'm getting at here is, if you know what you're doing and you can solve this equation, then you might find something that looks a little bit like this. This is a particular example of what a wave function might look like as a solution of this equation. It's a particular specialist example, but I'm showing you that we've calculated how the wave function changes over time. And again, I want to stress that this is completely deterministic. But what I also want to stress is what is actually evolving here is the amplitude. In other words, what we're saying is the pattern of amplitudes, which after all are determining the possible outcomes, that's what's changing. But still, nothing has actually happened. The evolving amplitudes still haven't turned a possibility into an actuality. That change of when the psi state turns into another state which has got property 1, or another state which has got property 2, or we find the electron at a particular place, or better, in a particular region at a particular time. That's not happened. This evolution of the state is still not causing anything to actually actualize, if I can phrase it this way. It's just how the pattern of possibility shifts over time. What that means is that we actually need another way in which states change over time. This is Chris Isham, who's one of my quantum heroes, and he has some very interesting things to say about this. So what he's saying is this: in quantum theory, another and quite different change of state can occur, and that's when measurements are made. This is the so-called reduction of the state vector. If you go back to my particular diagram, it's when that psi turns into either 1 or 2 or 3 or whatever. And what Chris is saying is this reduction of the state vector is one of 4 central problems around which discussions of the interpretation of quantum theory must rotate. And he actually puts a diagram in his book, which I've kind of adapted here. And those are the 4 particular interconnected issues which you must face if you want to come up with an interpretation of quantum theory. And I'm going to talk about a little bit about each one of these in turn. But Chris goes on to say this: within a pragmatic or a strictly instrumentalist approach to quantum theory, or if you want to put it slightly cruelly, shut up and calculate approach, you can just about avoid these issues with a clear conscience. But if, as Chris would do, I'm sure, or certainly as I would want to, if you want to move towards a more realist position, in other words, you want to inquire what quantum theory is telling you about the nature of reality, then these problems really become quite severe, particularly if you want to start saying that our state is describing an individual system, an individual electron. We've got to run into these problems with a major focus. So let's take a look at them. And seeing as we've already started a bit talking about state reduction, let's start with that. Now, let me just be clear. We've got this deterministic evolution, which is how our amplitudes change over time. That's fine. Quantum theory completely discusses that. The calculations are well known, well rehearsed. What we're talking about now is this change, this collapse of a set of possibilities into something that actualizes. And this is what we refer to as the measurement problem. What causes that to happen? How does that dramatic, sudden, non-calculatable, non-deterministic change actually take place? And it harks back to this thing I said earlier. Does the system actually have values before the measurement takes place? Or does the system have a set of potential, possible, kind of halfway intermediate nature of values, but then one of them gets picked out by random to actualize at the moment at which the measurement actually takes place? In which case, what causes that transition to happen? What causes the possible to become actual? What causes our initial state to suddenly snap into, collapsing into state 4? Now, as I said, traditional quantum theory has no account of that. This is not part of the equations. The Schrödinger equation does not predict this. Yet, we need it to happen. Otherwise, we can't get beyond all that quantum theory predicts is a range of possibilities. We can't measure the relative likelihoods of each of those possibilities to actually come about. Now, there's several options on the table as to what is actually causing this. First option is that actually, when I talk about the state of a system, I'm not actually talking about the state of an individual system. All a state can do is represent a large collection of identical states, an ensemble, if you want to use the technical term used in the trade. So when I talk about a quantum state, I cannot refer to the quantum state of an electron, but I can refer to the quantum state of 500,000 electrons, all of whom have been prepared in the same way. In which case, you could argue that when the state collapses, all that's happened is my information about the system has changed. Now, that's a justifiable and a tenet that people hold to. I have difficulty with it because, again, I want to seek out a realistic interpretation of quantum theory. I want the state to represent an individual electron and tell me something about what it is to be an electron. And I would say also that this idea that the state refers to only a collection of electrons, that kind of runs into problems because we know even a single electron traversing an experiment can be part of an interference pattern. And if a state refers to only a collection, that becomes hard to explain how that can happen. Another viable option, which some people adhere to, is to simply say, well, state collapse just actually doesn't happen at all. And this, in a sense, is the idea of the many worlds interpretation. So that when a measurement takes place, it's not that the state collapses into one or more of the possibilities. All the possibilities continue to evolve forwards, but what happens is they kind of branch out into separate decohering worlds, so that all the possibilities exist together simultaneously. But as time rolls forwards, so that the overlap, if you like, between these different possibilities breaks down and they kind of evolve into separate worlds. Now, clearly, there's a lot more technical explanation that has to go into that than I could possibly do in a few short minutes here. I'm just indicating that one solution to the measurement problem is to simply say, well, state collapse doesn't actually happen. What happens instead is that all possibilities happen at the same time and they gradually separate into separate worlds or universes, however you want to call it. Another clearly popular amongst our clientele here, and with good reason, is the interpretation which was developed by David Bohm and Basil Hiley, which is they referred to it initially as they developed the ontological interpretation as a better terminology for it. In which case, and in many ways, it sounds very, very similar to the many worlds interpretation, because the different measurement outcomes, they're referred to as channels. So these different channels actually do continue to exist all at the same time. And each of these channels contains information about the structure of the experiment as a whole, but actually the electron, if you like, or the system only traverses one of the channels. And that channel is not entirely picked out at random. If we knew precisely the initial conditions of the electron, we could predict which of these measurement channels it would actually traverse. But we can't measure the initial conditions of the electron precisely enough, and that is kind of where the randomness comes into the Bohm and Hiley interpretation. And whichever of the measurement channels the electron traverses, the information in that channel is active, and the information in all the other channels is inactive, and it kind of dribbles away or dissipates away in all of the other channels as this time evolves. So there's a few options, but there are more. One option, which is seriously talked about in certain quarters, is that the mind actually collapses the state. Because what people refer to, or what people draw attention to, is if a measurement is to make any sense whatsoever, sooner or later, it has to enter someone's consciousness. And that is the point, the supposition is, at which the actual collapse of the state happens. The moment that this state, the information, enters someone's consciousness. Now, this is something that we're going to revisit after the break, because I want to develop this thinking a little bit further and talk a little bit more about how experimental apparatuses entangle themselves with the measuring, with the thing that they're measuring, and how one device would entangle itself with another, etc., etc. So I'm going to develop that point a little further. But it's certainly out there as one of the possibilities that when the information in the measurement enters the consciousness, that is where the actuality, the manifestation, if you like, takes place. But that still kind of doesn't tell us how it happened. And it does open up some problems about, well, how did the world get along before consciousness arose? Now, John Wheeler has a thought on this. His suggestion was that we live in a kind of participatory universe, and actually observations that we make now can actualize the past. So it's kind of retroactively actualizing the past based on observations made now. And there's another possibility as well, which I kind of refer to as neo-Copenhagenism, which is that actually the collapse of the state will happen whenever the system interacts with some sort of large-scale measuring device. How yet that comes about is still a certain degree of mystery, but again, a little bit later, I'll develop the thought a little bit further. So we're not saying the state happens when it actually, the collapse happens when it enters consciousness. There is something about a large-scale system, a system containing a great deal of information, perhaps, that triggers the collapse of the state in some fashion. So the third category of options I want to consider is, for want of a better term, objective collapse. In other words, what this is saying is that the wave function is actually something real, not real in a mathematical sense, because we've already said it's a complex number. I mean, ontologically real. It is something that is ontologically out there, but it doesn't exist in the layer of reality that we wander around in drinking our coffee. It exists in an implicate layer underneath, because after all, it's a complex number, it's multidimensional, etc., etc. So it can't make itself known in our layer of reality, but it does exist in a world of what you might call objective potentiality. Heisenberg was a great fan of this idea, and he used the term potentia, which he'd coined from, not coined, half-inched from Aristotle. So he said that the wave function is an objectively real collection of potentia, which lie underneath our well-known reality that we rummage around in. In which case, the collapse of the state is actually a physical change in this amplitude in some fashion. Maybe, as I suggested earlier, some interaction with a complex system actually causes this physical change in the amplitude to take place. Something to do with information, perhaps active information, interacting with a less informed system can cause this to happen. Or Penrose suggests that there's actually something non-computable to do with space-time geometries that actually cause the state to collapse. He is suggesting a modification to the Schrödinger equation, which would predict collapse. Just in very quick outline, what Penrose is suggesting is these different possibilities that kind of simultaneously exist, you know, the electron being here, maybe, the electron being there, maybe, they have slightly different gravitational effects. And as the system evolves, as these amplitudes evolves, so these gravitational effects start to get more and more distinct from one another. And at some point around about what's referred to as the Planck scale, that those differences become unsustainable and something's got to happen. Something's got to trigger the collapse. And Penrose has suggested some experiments that we might do to check this idea. Okay, so there we are. That's a review of the issues to do with state collapse and the measurement problem. Now let's look a little bit about entanglement, which is another of Isham's quaternary of problems. Here's a quote from Schrödinger, who is the guy that coined the term entanglement. And what he's saying is, when two systems, which we would normally describe as using two completely different set of amplitudes psi A involving the position of system A at a particular time, and psi B involving the position of system B at a particular time, completely separate and distinct collections of amplitudes which describe the two systems completely well. However, if we allow these systems to interact with each other in some way, so and after the time of mutual inference, the systems separate again, then we find that we actually have to use a new state. And in particular, this state cannot be separated into the original states of the two systems. Something new has happened. It can't be factorized, if you like. It can't be broken down into a simple product of the two separate states. A merging has happened, an entanglement. Something new has entered. These systems now are entangled in one another, and that means that we can no longer describe them in terms of what were originally separate collections of amplitudes. They now, if you like, have a mutual collection of amplitudes. When two systems are entangled, their combined state cannot be separated into states for each system separately. What this means is that if we have our two entangled systems and they separate out and they come across two measuring devices, Alice and Bob, so that particle A gets to Alice and particle B gets to Bob, and you'll notice that Alice is a little bit nearer to where the particles are created than Bob is, so that particle A is going to get to Alice before particle B gets to Bob. And so if Alice's device measures particle A, it's going to cause some collapse, but not of the separate collection of amplitudes belonging to A, because in a sense, they don't exist anymore. It's going to cause a collapse of the mutual amplitude that's involving both A and B. In other words, the measurement made at Alice is going to collapse the state of both systems, and so impact on the later measurement taking place at B, even though there is no time, if you do your experiment well, for any signal to get from Alice to Bob. So how does this mutual collection of amplitudes, how can it give rise to a correlation between the behavior of two systems, even though they are separated by some distance? And I think a clue there is perhaps we shouldn't be thinking of them of two systems anymore. They are just one mutual system. And our fourth problem is the problem of, in quantum mechanics, the problem of probability. So we've had state reduction and the measurement problem. We've had the issue to do with entanglement. Now we're going to talk about probability. And this harks back to something I said a little bit earlier when I was referring specifically to quantum probabilities. I want to tease that out a little bit further now. Because it's not like we don't frequently use probability in physics. We've been using probability in physics well before quantum theory rocked up. Generally, we use probability, well, if we don't have enough detail to calculate exactly. You know, we don't have enough detail to know what the weather's going to be like tomorrow, so we can't calculate exactly. There's good reasons why we can't do that as well. It's a bad example. But the other possibility is that actually we've got too much detail. If you're studying a gas which has got something like 10 to the power 20 particles or more in it, you're not going to be able to keep track of what each of the so-and-sos is doing. So the best you can do is actually discuss what the particles are doing on average. And the minute you start saying things like on average, then you've snuck probabilities in kind of by the back door, because you're calculating what is most likely to happen. Now, the key point here is, in all of these cases where we've used probability in the past, it doesn't mean that an exact calculation isn't possible in principle. It doesn't mean that the laws of physics are not actually determining exactly what's going on. What it means is either we haven't got the computational power, or frankly, the inclination to keep track of all 10 to the 20 particles, or we don't have enough information about what all of the 10 to the 20 particles are doing in order to make an exact calculation possible. That doesn't deny the possibility of doing it. It's just saying that in practice, it's not possible. And these are what I refer to as classical probabilities. In other words, we're using probability to mask or to support our ignorance or our lack of ability to do the exact calculation. We're not saying you can't do an exact calculation. We're kind of saying we can't be bothered. Whereas quantum probability, that's very different. Or at least some probabilities in quantum theory are. You do get some classical probabilities here anyway. It's a thing called the density matrix, but that's an entirely different conversation. Let's go back to the Born rule. When we square our amplitude in order to calculate the probability, this is a fundamental probability. It's the best we can do. Remember I said the state is the collection of all possible information about the system. That possible information boils down to what are the probabilities that it will do something else. And those probabilities are there not because we don't understand the physics well enough. It's because there is no such physics to determine exactly what's going to happen. The physics is not there. Einstein dreamed of a hidden variable theory, as he called it, the idea hidden being that we haven't yet discovered enough information about our systems. And if we knew these variables that we don't know now, we'd be able to calculate exactly. Well, we have pretty good grounds for believing these days that even if a hidden variable theory did exist, the constraints on it, in order for it to match the predictions of quantum theory, would be such that the hidden variable theory would be even worse. So these are fundamental quantum probabilities. They do not mask our inability to do the calculation. They tell us there isn't a calculation. That's why the collapse of the state is not predicted by the Schrödinger equation. The collapse of the state is not calculable from the Schrödinger equation. The particle, the system, has the potentia to be in many places, and we can calculate what those potentia give rise to in terms of probabilities, but that's it. So what's the problem? The problem is, what do we mean by a probability? If I say to you, here's a well-engineered dice, a six-sided dice, the probability of one side coming up is 1 in 6. Well, why is it 1 in 6? Well, it's 1 in 6 because, duh, the dice has got 6 sides. But what is it about the quantum system that gives it a probability? What is the, for want of a better way of phrasing it, what is the shape of the quantum system that gives it a probability? Well, it's the amplitude. The amplitude is what's giving it the probability. So we're really talking about, what is this amplitude? We know if we square it, we get a probability. And we know, therefore, that the shape of the amplitude is determining the probability, a little bit like the shape of the dice is, but not really, because we've got to square the amplitude in order to. So what is really, and I use the word really here very pointedly, what's really going on? What are these quantum probabilities? What do they tell us about the nature of reality? Now, I want to step away for a moment from Chris Isham's 4 sets of problems, as if they weren't bad enough. But what I do want to bring into now is to discuss the uncertainty principle with you. Because this is, in a sense, projectable out from Chris's 4 problems, but it puts a kind of different slant on things, maybe. Now, let's be clear. Whenever you take a measurement of anything, whether it's quantum or not, you never get the same result twice, unless it's kind of by blind luck. Why? Well, because it's very hard to reproduce systems in exactly the same way. If we're going to check out that we've measured things correctly, you need to measure n of them and check the measurements against each other. And it's quite difficult to make sure that all n of them are prepared in exactly the same way. So you get fluctuations. You get some fluctuations in your measurement device. The measurement device's properties might change a little bit from one measurement to another. Or maybe something in the environment is impinging on the measurement in some way. You're trying to make a measurement of something and someone's bouncing on a trampoline next door. Inconvenient. But in classical physics, none of this mattered because the effects were too small and you could kind of correct for them anyway. But then we run into quantum theory and our wave function. Now, as I've said, the wave function is giving us the idea, the probability that we're going to find a particular particle in a particular region of space. The best we can do, in truth, is kind of constrain it. We're never going to find it exactly at an individual point. We're just going to take a whole load of measurements, and when we take the measurements, we're going to find it clustered around some average within some region, which I've called delta X there. Sorry to put a graph on the screen. I know some of you don't like graphs, but just think of the shape of the diagram. Basically, what I'm saying is my measurements are all clustered in a hump, but the hump has got some width because I'm never going to get the same result quite all the time. After all, the probability of finding anything in an exact infinitesimal spot is 0. So all we can do is say, we're going to find it within a region. Now, Heisenberg talked about something called the gamma ray microscope. How are we going to set about measuring the position of an electron? And he used this analogy or thought experiment, if you like. And this is what he said. If we want to clearly understand what is meant by position, then we have to indicate how we're going to measure it. I'm paraphrasing here. If we want to know what we mean by position, that term position only has a meaning in the context of the process by which you're going to measure it. Otherwise, it's meaningless. And he suggested, okay, let's imagine we've got some really powerful microscope, and we need to use gamma rays in order to do this, to illuminate the electron in order to find out where it is. Now, notice what we're doing is we're firing in a gamma ray photon. It's going to bounce off the electron, turn into that red squiggle. We're going to pick it up in some lens. That's the thing marked D at the top. And by focusing in, we're going to see where the electron is. But we don't measure the incoming photon. Yes, we generate a laser. We tune the laser to be a particular energy. But that doesn't mean it's going to be exactly that energy. We don't know exactly what energy that photon is coming in at. And when the photon hits that electron, it's going to cause that electron to recoil. In other words, it's going to change the momentum of the electron in a way that we can't completely compensate for, because although we might be able to measure the energy of the photon that we detect, the red one, we don't know the energy of the incoming photon. So we can't determine exactly by how much the momentum has changed. Heisenberg said, at the instant of the determination of the position, when the light quantum is diffracted by the electron discontinuously changes its impulse. That's what he's using the word impulse to mean momentum there. The change will be more pronounced the smaller the wavelength of the light used. In other words, the more precisely we try and measure the position, the more we're going to muck up the momentum. That brings us back to amplitudes again. Now, if we're considering our amplitudes, and I'm going to come back to the gamma ray microscope in a second, then we can do one of two things. Again, think of this as the amplitude for an electron. We can specify that my electron has got a certain energy and a certain momentum, in which case our amplitude will tell us how the electron's position, will tell us how the amplitude varies with position and time, given the energy and the momentum we specified. That's one thing we could do. Or we could say the position of the electron at a particular time, and then we could track the amplitude over a range of different energies and momentum. In other words, we can express the amplitude for a certain energy and momentum by making it free across space and time, or we can express the amplitude for a certain position and time by letting it be free across energy and momentum. Well, in practice, we tend to do a little bit of both. In practice, what we tend to say is we're going to constrain the momentum to a particular range, we're going to constrain the energy to a particular range, we're going to constrain the position to be a particular range, and we're going to constrain that. Oh, how do you constrain time? Need to come back and think about that. Right, so let's get to the nub of what I'm trying to say here. As it turns out, because of the Schrödinger equation, amplitudes are connected to each other. In other words, if I do constrain the momentum, in other words, I say my electron has got momentum very tightly controlled, then the amplitude for its position, woof, I can only constrain its momentum by allowing the amplitude for position to really spread out. The probability that I will measure the electron to have a momentum within that tiny range causes the probability to measure the position to really spread out across a wide range. And vice versa. If I do a different experiment where I constrain the position of the electron within a tiny region, then I can only cause the momentum to spread out across a large possibility. And that's Heisenberg's uncertainty principle. In other words, the more you tighten the screw down on one thing, the more the screw loosens somewhere else. You can't tighten both screws together. Why not? What is it again about the nature of amplitudes, the nature of reality, that prevents this from actually happening? Also, by the way, there is what I call the energy-time inequality. And that's sometimes expressed as an uncertainty relationship. And many horrors have been perpetrated in the name of the energy-time uncertainty relationship. It is not an uncertainty relationship. There is a technical reason for this, which I'm not going to go into, but if you're interested, there is no time operator in quantum theory. How would you have something that had pinned down a time? You can have an operator for energy, an operator for position. You can't have an operator for time. This is not an uncertainty principle. So what is it? That delta t is a duration, not an uncertainty about a particular time. It's a duration of time. The way we should really be thinking about this is this. Imagine I've got a system which is evolving, and the value of the variable I'm measuring changes from Q1 to Q2. How do I know it's changed? I only know it's changed if my measurement results, the two humps I get, are sufficiently spread out that I can distinguish that there are actually two peaks there rather than one. And that, it turns out, is constrained. You have to measure, you have to allow the system to evolve in quantum mechanics over a certain duration, delta t, in order to get a distinction between the two values sufficient to resolve their difference. And that is the energy time uncertainty principle. In other words, you can't tell that the energy has changed by an amount delta E unless you allow it to evolve over a period of time delta T. Anyway, I don't want to go on about that particular hobby horse in too much detail, because again, maybe I'm straying onto a little bit too much mathematical detail for many people's tastes here. I just want you to know that if someone tries to sell you that something about borrowing energy for a certain degree of time and paying it back again, don't buy it. They are trying to sell you a hobbled horse. Yeah. But the big question really here, again, is this uncertainty principle something that's in nature? In other words, because we're saying we can't constrain the position except within a range delta X, does that mean the electron does not have a position until such time as we come about measuring it? They get manifest at the time which we make the measurement. Or is it simply epistemological? In other words, the gamma ray microscope, that doesn't say the electron didn't have a position before we measured it. It just means you can't exactly measure it. It's got a position, and we just can't be entirely sure what it was before we took the measurement, and the measurement constrained it to within a particular region. That's kind of more the Bowman-Hiley approach. It's more about our ability to measure something rather than something that's actually ontologically happening in the world. They talked in terms of position being a hidden variable for the electron. I think possibly they regretted using the word hidden there. I think they might have been better off using a word like veiled. In other words, we can't quite pin down where the electron is, but it is somewhere, would be their approach. Whereas the ontological one, the kind of one that I'm selling, is the electron. It's not that we don't know what the position is before we measure it. It doesn't have a position until we measure it. The concept of position is not appropriate until the measurement. Right, so there we are. We've had a quaternary of problems. I've yabbered on for a little bit less than an hour. I think what we now need is a quaternary of coffee memes. I think this would be a good moment to take a short break. What do people think?
Yeah, I think that's a great idea, Jonathan. Thank you so much. So let's take a 10-minute break. We'll come back 10 minutes after the hour. And yeah, we look forward to seeing you all then. Thank you, Jonathan.
If, by the way, I'm preloaded with coffee. I've taken the liberty of providing myself.
What about water? Water works as well.
Hello. This is so what I was going to say was, if anyone wants to discuss, or they don't need to run off for a coffee break, if they want to discuss for 10 minutes or wildly contradict what I've said, by all means,
yeah, if anyone wants to come in, then maybe use the raise your hand function, and we can just kind of open it up for a very casual discussion now if somebody would like to come in.
Yeah, nothing of too much import, because those people who have actually gone off.
Yes, exactly. Let's leave the good questions for later. But if anyone has any comments or anything they'd like to share at this point, please feel free to come in during this 10-minute break. Sperry, come on in.
Well, thank you so much, Jonathan. This is an excellent presentation.
Thank you.
I hope you can hear me.
I can. It's a little bit muffled, but I can make you out.
Okay. So,
That's
as
better.
you know, David Bohm had this sense that there might be an implicate order that was actually organizing and orchestrating what we're measuring and finding. And he hoped that that it wasn't a particle, it was rather something that would be so infinitely precise, that was underlying the wholeness of the universe,
Yeah.
that was what was causing the all these phenomena to be found and measured as you're speaking about. What would you say about the finding that implicit ordering that might underlie all this uncertainty and probability?
Firstly, I've got to say I'm quite excited. In a week or so, I've got the opportunity to spend a day chatting with Basil Hiley. So I'm going to chuck some of these questions directly at him. I've kind of pinched the term implicate order, and I hope I'm using it, and this is what I want to check out with Basil, in a sympathetic way, because my own personal view is I subscribe to the idea that the amplitude isn't ontologically real thing. It does exist out there, but it's in a layer of reality underneath, the reality that has coffee mugs and couches and video cameras in it. And it is this implicate layer, which is where the amplitude actually lives. And it's the underlying business of this implicate layer that gives rise to, I guess he would use the term enfolding and of actualities out of that. So I have a great deal of sympathy for that approach. As far as my understanding of the history of their thinking goes, the original papers talk very much in terms of particles and the quantum potential that helped steer the particles through the various interference experiments to end up at particular places. But their thinking very much developed beyond that, because they were aware that the ontological approach to quantum theory, which is particles and the quantum potential, when we talk about quantum theory, we tend to forget that actually quantum theory has been supplemented or supplanted by quantum field theory. And quantum field theory is the true quantum theory. Quantum theory is a kind of a limited approximation to quantum field theory. So they pushed their approach into the field theoretic regime as well, in which case there is now something called the quantum superpotential, which gives rise to manipulating fields. And that basically, I think I'm right in saying, I'll check it with Basil, their view of what a particle would just be kind of like a concentrated region of field. I think in similar terms. I talk about a ruck in a carpet. When you lay your carpet, at least whenever I lay a carpet, which admittedly isn't often, but whenever I lay a carpet, there's always some crease in the blooming thing. And if I push it down here, it pops up over there. And that's kind of the way I think about particles. So, if we measure the particle to be here, we squash it down and boom, it pops up over there. Doesn't mean the particle actually traveled from here to there. What it means is the particle manifested itself here, then folded away again and enfolded out again over there. And we kind of interpret that as being it traveled from one to another. But in field theoretic terms, kind of it didn't. So I don't know if this is helping at all, but fundamentally, I'm very sympathetic to the philosophical approach. Whether their actual technical way of dealing with quantum theory is more correct than the other technical ways, I'm not sure. I kind of also agree with, I think, something that Basil once said, which I've kind of taken on board as a bit of a mantra, which is the fact that we have so many different interpretations of quantum theory. That kind of tells us that we haven't got the concepts right. Because surely if we had the concepts right, the theory would probably tell us its interpretation. So the fact that we have these interpretations, I think, is probably a signal that we're not quite there yet. Anyway, I think I probably rambled a bit too much there, but hopefully a little bit of love of your question.
Why don't we let Gary come in and ask his question, because
Thank
we've
you
only
so much, Jonathan.
Can we restrict Gary to a mere 1,000 words?
Yeah. Gary.
So
Alfred, how are you doing, mate?
I'm doing great. How are you?
Good, man.
So I was hoping you'd say something about the transactional interpretation. You did say something about Wheeler's participatory universe, which I think is absolutely critical, because what it implies is that we are part of what we are observing. We are embedded in the world we are observing, and because of that, there is a loop. There's a time loop. right? There's going to be a delay between what the act of observing and what is being observed, and the fact that there will be some influence of the act of observing on what is being observed, right? And that's unavoidable. And I think that idea, in some sense, is captured in the transactional interpretation from Kramer and Kastner.
Yeah.
Right. I mean, which says that.
I'm pretty straightforward and honest with you, which is that the reason I've not really talked about the transactional interpretation is I'm not confident I understand it well enough to talk about it at this point. So it's kind of on my to-do list to dig into it a bit deeper. And I've kind of learned from 30 years of being a teacher to try and not talk about something if you don't fully understand it yourself as yet.
Okay.
So
that's fair enough, Jonathan, but I would encourage you to go and learn.
No, it's on my to-do list, but as you know, there's a book on entropy that needs killing off first.
Okay. All right.
Thanks, Gary. It's great to see you. I don't know if anyone, well, we have 2 minutes left. I don't know if anyone else wants to come in. Please, Raymond.
What do you think? Which is the best coffee meme? Do you think? I'm a fan of the one.
Raymond might have an answer to that.
Oh, I don't know about that. Can you hear me? Can you hear me?
Yeah.
Perfectly.
Okay. Please excuse my ignorance. Much of this is over my head. I'm a poet, not a physicist, but I've read quite a bit of David Bohm and other theoretical physicists, but with very limited understanding. So listening to the presentation, I'm trying to get the sense that a machine determines a momentary position for an electron that after the measurement actually no longer exists, but it can never actually determine the holistic path of the electron itself. In other words, machines then are incapable of measuring the path of an electron. Do I have somewhat of a sense of being correct there, or?
Well, let me try and tease it out a little bit further. A machine is a measuring device.
Right.
All we know from the mathematics is that we know we can calculate this very strange thing that we call the amplitude. And what are we to make of that amplitude? Well, what we're to make of it, apparently, according to the Born rule, is it tells us what the probability of something popping up in one of our measurements is.
Right.
It only tells us the probability of this thing popping up. Now, when we actually make a measurement, one of the possibilities actually pops up, but we can never tell which one it's going to be. So somehow or other, this amplitude determines what the range of possibilities are and their relative likelihoods, but it never tells us what's actually going to happen. And that's the lacuna, that's the gap. How do we get from our physics, which is describing the range of possibilities, to something actually manifesting, something actually happening? And that's what's called the collapse of the state. The possibilities, something actualizes. Now, what causes that to happen? We don't know. That's the measurement problem. It's one of the fundamental problems in science. And, you know, if you're interested in what science is trying to tell you about the nature of reality, then it's a big problem. It's an obvious, huge hole. Lots of my colleagues who are professional working physicists just get on with their lives and don't worry about it. That I couldn't cope with. I worry about that. So what causes it to actually happen? And one of the possibilities is simply the interaction between a nice, simple little thing like an electron and a whacking great particle accelerator detector like you find out at CERN. Something in that interaction, the machine, if you like, causes one of the potentials to actually actualize. We don't know how. We're just trying to wave our hands in what might be a fruitful direction of research. So that's one possibility. Another possibility is that when it enters the mind of the experimenter, that's what causes the collapse to happen. Another possibility is that the collapse never happens and our worlds just branch out into different parallel worlds like that. So we're trying to bridge a gap. We're trying to come to some understanding of what is actually causing what all we can describe in the mathematics, the range of possibilities, to become the actuality, which is what we observe. And it might be a machine that's causing it, or it might be the mind, or it might be just that we're in a parallel world. All of these things are on the table. Now, to come back to what you were saying about the trajectory of the particle, well, in a sense, we never do measure the trajectory of a particle. We just say we know it's here now, and it's there then, and it's there then, and we kind of mentally draw a line and say that's the path the particle went over. I don't know if you've ever seen some of these gorgeous bubble chamber photographs you can see with all sorts of spirals and swirls and particles flying all over the place. Yeah. And you look at one of those and say, oh, look, there's the track of the particle. It isn't. That isn't the track of the particle. What you're seeing is a collection of little bubbles, tiny little bubbles, you know, in a line. And what's happened is that the particle has caused a bubble to appear here and caused a bubble to appear there and caused a bubble to appear there. Each of these bubbles is kind of like an individual measurement of where the particle was. And we, again, our eye draws a line through them. We say that's the trajectory of the particle. But we measure it to be at that bubble, and we measure it to be at that bubble. Then we don't know what the hell happened to it in the meantime.
It's kind of like reminds me of early animated films where they just drew individual frames and put them together.
Yes, exactly. Which is why an author of this parish talked about flickering reality a lot.
And another question that just came to me.
I don't know, Jonathan, do you want to finish your presentation first? And then
I think if you don't mind, I'd love to.
And then Raymond, we can come back to you as soon as we're finished.
Fantastic. Thank you so much.
Thank you, Jonathan. I think we all wish that we had you as our physics teacher. So anyways, please carry on.
Okay, right. So I promised I was going to talk about wholeness. So let's go. First half has been a little bit of a primer about quantum theory. Hopefully I didn't lose everybody completely in that time. Hopefully I've given you a little bit of a taste of quantum theory. And now we can start to look at these books and what they said. But before we do that, I want to make a point absolutely clear. I've picked out the Tower of Physics and I've picked out the Dancing Wooly Masters. And I'm going to be, I was about to say slightly rude about them. That's not fair. I'm going to take a more critical approach to them. I think they were hugely important, very influential, beautifully written books. I'm a big fan of the Tao and a big fan of the Dancing Wooly Masters. I read both of them when I was a kid. I'm absolutely sure the Tower of Physics was a very great signal post on my way to doing a PhD in particle physics. I owe that book an awful lot. I think they were very well-meaning books, and I think they caused some very useful conversations to happen. But I think they may have overplayed their points a bit, particularly if we look back in hindsight now, the kind of things they wanted to say. And so I want to pick up on this and suggest some more nuanced approaches. So kind of on this page here, I've got a couple of quotes from Fritjof Capra, and I've kind of highlighted in yellow where I'm kind of agreeing with him, and in blue where I'm kind of saying, yeah, I'm not too sure about this. So on page 68, he's saying, quantum theory reveals a basic oneness of the universe. It shows that we cannot decompose the world into independently existing smallest units. I'm on board here. I think this is to do with entanglement. As we penetrate into matter, nature does not show us isolated building blocks, but rather appears as a complicated web of relations between the various parts of the whole. I'm on board there, because didn't I say that you can consider the amplitude describing our system as a set of possibilities reaching out? So I think I'm on board with that. These relations always include the observer in an essential way. The human observer constitutes the final link in the chain of the observational process. Well, maybe that's so if you buy the mind causes collapse. But if you don't, and that's only one of the possibilities, then I'm not sure we can justify that statement completely. Anyway, let's move on. And the properties of any atomic object can be understood only in terms of the object's interaction with the observer. Well, Heisenberg was saying the word position only makes sense in the context of a description of how you're going to measure it. Yeah. The observer didn't come into that. Okay, maybe the observer chooses to measure the position. Maybe the observer chooses the process by which, the particular way in which we're going to measure the position. But again, the actual measurement is done by the machine. Okay, well, page 69. The Cartesian position between the I and the world, between the observer and the observed, cannot be made when dealing with atomic matter. In atomic physics, we can never speak about nature without at the same time speaking about ourselves. In modern physics, the universe is thus experienced as a dynamic, inseparable whole, which always includes the observer in an essential way. I'm not sure it does. In this experience, interesting use of the word experience, the traditional concepts of space and time, isolated objects, cause and effect, lose their meaning. I'm on board there. After all, remember what I said. The state collapse is not predicted by the Schrödinger equation. The state collapse, there is no physics that determines what will happen and when it will happen. The best we can determine is the possibilities. Now, I didn't use the phrase, but actually what we're saying is there is no cause for the state collapse. It just happens. There is no prior cause that will make it happen. And this is one of the things that Einstein really hated about quantum theory, because he bought into the chain of being, the web of cause and effect. And quantum theory puts a spade through it. So I'm on board with what Capra is saying there. I have to confess, I meant to go back and see if I could find a couple more quotes from Gary Zukov, but I've only just come up with this one. It'll do us. The new physics, quantum mechanics, tells us clearly that it is not possible to observe reality without changing it. If we observe a certain particle collision experiment, not only do we have no way of proving that the result would have been the same if we'd not watched it, all we know indicates that it would not have been the same, because the result that we got was affected by the fact that we were looking for it. Well, I'm not sure I would go along with the stress there. Okay, let's go back to the source. Let's go back to see what Bohr had to say here. Now, the first thing you have to say is, I think somebody once I can't remember who it was. Someone once said about Bohr, his thinking was clear. It was just his writing that was incredibly obscure. And I think if you try and read Bohr, you need to read it a few times to kind of get the sense of what he's trying to say. Anyway, this is what Bohr had to say. This is actually the first one is a quote from his paper, which was his rebuttal of the EPR paradox published by Einstein, Podolsky, and Rosen. Indeed, the finite interaction between the object and the measuring agency, I'll do a little translation as we go along. The finite interaction between the object and the measuring device, conditioned by the very existence of the quantum of action. Bohr was incredibly vague about what he meant by the quantum of action. Come back to it in a second. The impossibility of controlling the reaction of the object on the measuring instrument. In other words, what he's saying is, go back to that gamma ray microscope. We can't measure exactly what the energy of the incoming photon was. We can measure what energy this was. We can measure what the momentum of the electron is, but because we can't determine this exactly, we can't exactly determine the momentum change of the electron. In other words, we've kind of fuzzed it up. This necessitates a final renunciation of the classical idea of causality. Now, the quantum postulate, again, he's not clear what he means by that. It kind of relates to the quantum of action, and it kind of relates to this idea that there's something going on when a measurement interacts with when a system interacts with a measuring device. The actual details of that interaction We can't know because they are not themselves part of the measurement. We can insert another measuring device, would enable us to figure out or help figure out what's going on when the first measuring device interacts with the system. But that second measuring device that we've put in, we don't know how that interacts with the other two. So there is always a bit that we don't know about, a lacuna in there. An independent reality in the ordinary physical sense can neither be ascribed to the phenomena nor to the agencies of observation. They are connected in the process of measurement in a way that we cannot completely define, nor can we completely describe, unless we put another measuring device in to help us describe it, but in which case that measuring device has an indescribable connection. Every measurement involves an interaction between the thing being measured and that doing the measurement. And that interaction cannot be completely measured nor completely controlled. If we tried to do that, we would actually change the original experiment. Any attempt to measure the interaction would introduce a new device, which will interact in an uncontrollable way. There's another way of thinking about this. If we consider a measuring device, any device that's going to accurately measure something for us has some basic requirements. It must be in some kind of initial state. The measuring device must initially sit in some ready state. I'm ready to have a measurement. I'm ready to do a measurement better. And it must have a set of states afterwards. That something about the device has to change in order to record the fact that a measurement has happened, and basically to tell us what the result is. If you like, there's a pointer, and beforehand it's set to 0, and afterwards it's going to be set to some value, which tells us the result. Now, these separate states which tell us the results can't overlap. They must be distinct from one another. If they overlapped, then we wouldn't know whether it was 1 or 2 because it would kind of overlap between the two. And they must be stable. We don't want the measurement to be saying, yes, I'm 1, but if you come back in 5 minutes, I might be 2. The measurement's got to be stable. These are basic requirements that we need. And if the measurement is actually going to correctly measure the particle, there must be a correlation. If the particle is in state M, then the measuring device must be in state R, where R is telling us that the particle was in state M. The process of measurement takes the initial particle state, which may be something that looks like that, and the initial device state, here we are, the particle state multiplied by the device state, that's my combined state of the two beforehand. Notice it's a product of the two. This isn't an entanglement. But when the measurement has happened, the two become entangled. Now, let me allow me to read this for you, because I understand that if this is not your native language, this looks incredibly complicated. But just look at the first one: A1 times state 1 times psi 1. What we're saying is, after the measurement, if the particle is in state 1, then the device must be in state psi 1, which is the state of the device that records the fact that the particle is in state 1. Or if the particle is in state 3, the device has to be in state psi 3 to tell us that the particle is in state 3. But the device has now become entangled with the particle. That gobbledygook mathematics I've written there is not separable into something to do with the system and something to do with the measurement device. They become entangled. And all we can say, if we're going to describe the measuring device using quantum theory, is after the measurement, the state of the combined particle measuring device has amplitude 1 to be in state 1 and measuring state 1, or amplitude 2 for the particle to be in state 2 and measuring state 2. In other words, the quantum description, again, doesn't tell us what's going to happen. It doesn't tell us that the measurement is going to record state 2. It just gives us this set of possibilities. State collapse of both the device and the system has to take place in order for something to actually actualize. The entanglement between the device and the system is, if anything, made the problem worse. It's made the notion of state collapse more critical. The final state means that the particle and the device are entangled together. They can no longer be thought of as two separate systems. They have a mutual set of amplitudes. Okay, so we've got this measuring device particle conglomerate that's in some sort of amplitude state. And again, we don't know what's actually going to happen. Right. Well, I'll use a measuring device to trigger the collapse. In other words, I will measure my measuring device state system. Well, that's going to become entangled as well. And all that's going to happen is that if we look at the device, our quantum state's going to become entangled as well. It's going to spread like a disease. Things become entangled with each other, and the entanglement grows and grows and grows and grows. Again, the state collapse, the manifestation of one thing, just hasn't yet happened. So where does it stop? Well, come back to what I mentioned before about neo-Copenhagenism. Bohr, the system to which the quantum mechanical formalism applied is, of course, possible to include any intermediate auxiliary agency employed by the measuring process. What he's saying is we ought to be able to describe the measuring device quantum mechanically as well. But if we do that, then it becomes entangled with the system. Okay, we'll solve that by introducing another measuring device, but shouldn't we be able to describe that measuring device quantum mechanically as well, in which case it gets entangled? But Bohr's got the way out. Some ultimate measuring instrument must always be described entirely on classical lines, kept outside the system, subject to quantum mechanical treatment. In other words, what he's saying is sooner or later you've got to stop using quantum theory and instead using classical physics, and that breaks the entanglement. That causes the state collapse to happen. At some level, a device must be treated classically, and that is where the entanglement stops. But that's not wholeness. That's the opposite of wholeness. That's drawing a line across the world and saying this side of the line, we use one type of physics, and the other side of the line, we use a different type of physics. That ain't wholeness. This is referred to as the Heisenberg cut. In other words, what we're saying is our quantum stuff, we can only do anything with it if it's embedded inside something classical. Sooner or later, we have to resort to classical physics. Otherwise, quantum physics is never going to get us anywhere. And the boundary between the two is what is referred to as the Heisenberg cut. It's the line at which you say, right, I surrender. I'm going to stop using quantum mechanics. I'm now going to use classical physics. Well, where do you draw that line? Bohr says, measuring instruments using rigid bodies sufficiently heavy to allow a completely classical account of their relative positions and velocities. In other words, he's saying a measuring device where we can use classical physics. Yeah, but that doesn't kind of tell us where that is. So it's not entirely helpful. But again, the real point here is if we're going to solve this problem, it's not going to project wholeness. It's going to project division. What about the mind triggers state collapse? This is often used. I came across this the other day. Quantum physics and the power of the mind. Find out how quantum physics and the law of attraction can change your life. Right. Now, Okay, so if we're going to subscribe to the mind causes state collapse, well, okay, I'm on board with that to some degree. But again, that's not wholeness. It's drawing a boundary between the physical and non-physical. We're saying everything physical can be described by quantum mechanics, but if quantum mechanics is going to work, there has to be a non-physical mind not described by quantum physics, which is going to cause the state to collapse. And again, that's not wholeness. That's not embedding the mind in nature. That's actually putting a distinct cut between the mind and nature. It's not integrating the mind into physics. And in any case, it's still not telling us how the collapse happens. It's kind of brushing it under the carpet, brushing it under the neurological carpet, you might say. And how did the world get on without consciousness anyway? Well, okay, maybe it was panpsychism, maybe it was Wheeler's retrocausality, or maybe we've got a kind of promissory transcendentalism. In other words, again, my worry about this is that we're pushing the problem into consciousness in the hope that at some point in the future it'll be solved there. Okay, maybe it will. But my point is still that even if this is the correct solution to the problem, it's not wholeness, it's a division. And anyway, isn't the whole idea of state collapse completely against, or completely, not against is the wrong phrase, it's at variance with the whole nature of the flow of the Tao? Isn't quantum theory actually more about discontinuous change? Isn't quantum theory itself, in many ways, more about discontinuity? We talk about quantization, we talk about transitions, we talk about state collapse, all of which are integral parts of quantum theory. Doesn't sound like very holistic language to me. Now, of course, there is an honourable exception to this, which is, David Bohm and Basil Hiley's interpretation, their ontological interpretation, because actually, as I mentioned earlier, state collapse doesn't actually happen in their approach. It's a little bit like many worlds, all the different measurement channels, but they don't separate into distinct worlds. It's all the one world, but these different possible measurement channels exist simultaneously, but the particle or the system only traverses one of them. We can't know exactly which one beforehand because we can't pin down enough information about it to start with. And there is the quantum potential. It's a very attractive approach to quantum theory because the quantum potential is informing. It's informing the way in which the particle moves. It's active information and it's contextual, which is a very important aspect of quantum theory. It's not an aspect I've dwelt upon so far. I'm going to revisit again in a couple of minutes. And as I've mentioned in the discussion at midway, we've got this quantum superpotential, we've got the quantum fields. And what does David Bohm say? Centrally relevant change in the descriptive order is required. The dropping of the notion of analysis of the world into relatively autonomous parts. Now, I buy that anyway, because I buy that to do with entanglement. The whole point of entanglement is that once the two systems have become entangled, you can't really think of them as two separate systems anymore. They become kind of a merged thing. Rather, the primary emphasis is now on undivided wholeness in which the observing instrument is not separable from what is observed. Now, you might think I'm being a bit unfair here, because isn't this just like the quotes from Zhukov and the quotes from Fritjof Capra earlier? Yes, it is, but I'm prepared to give David a bit more slack in this regard, because in the context of his approach, I think these are quite reasonable things to say. I'm not sure they're reasonable things to say within the context of a neo-Copenhagen mind causes collapse, that sort of approach to quantum theory. The description of experimental conditions does not drop out as a mere intermediate link, but remains inseparable from the description of what is called the observed object. He's echoing Heisenberg there. We can't describe it unless we describe how we're going to measure it. The form of the experimental conditions and the meaning of the experimental results have now to be one whole, in which the analysis into autonomous existent elements is not relevant. Okay. So I've kind of put a slight corrective on what Zukov and Capra and, you know, the industry of similar books, again, mostly all well-meaning, that was generated in their wake. I'm kind of put a bit of corrective on that. Let's try and be a bit more positive. What can we say? What can we definitively say that quantum theory is telling us? Kind of interpretation neutral, shall we say? Well, I think we can reasonably say entanglement radically undermines the notion of reductionism. That when particles, systems become entangled with another, which seems to be part and parcel of the process of what goes on in quantum theory, confirmed by experiment, and it is no longer possible to think of them in terms of the separate parts anymore. They've melded into a whole which has properties that couldn't be predicted from the properties of the parts. And if that's anti-reductionism, not anti-reductionism, well, I'm not sure what is. What else can we say? We can say that quantum theory is contextual. Now, what do I mean by that? What I mean is the complete specification of the experiment matters. Now, I don't know how many of you in the audience right now were unfortunate enough to see one of my earlier presentations when I talked about the ontological interpretation. And I showed this diagram now, and I'm going to try and quickly explain what it means. This is what's called the Mach-Zander interferometer. Basically, it's an interference experiment. And we shine a laser in, there's a collection of mirrors, and at the far side, there's two detectors, D1 and D2. And we find, ignore D3 and ignore this thing here for the minute, just focus on these two guys. We find that if this is properly tuned so that this length is exactly the same as this length, then we never pick up any light at detector D2. It only ever pops up at D1. There is an interference between the waves traveling along that path and the waves traveling along that path, which destructively interferes, meaning no light gets here and the only light gets there. Now that gives us problems when we think about photons as particles, because, you know, the photon's either got to go that way or it's got to go that way, or in some sense, it's got to traverse both possibilities at once. But what do I mean about the contextuality? What I mean is this. If you pop in another mirror here, which you can switch on and off, so there's another detector there. If the mirror is switched off, then the photon could go that way or it could go that way, and we've got interference. If the mirror is switched on, the interference goes. Whether the photon went that way or that way. So even if if the photon goes this way, it's going to hit the mirror and get to D3, so it's never going to pop up at either D1 or D2. If it pops up here or there, it must have gone that way, in which case, how the hell does it know that the mirror was there? And that's what I mean by contextuality. The complete experiment matters to every aspect of the system. And that's what is captured so really nicely in the quantum potential. The switchable mirror destroys interference. The context of the whole experiment determines the outcome. And let's come back to the nature of amplitude. So I think quantum contextuality, which is we live in a contextual universe. We live in a fundamentally non-reductionist universe. We live in a contextual universe. What about the nature of amplitudes? Amplitudes as tendencies to become. I think that means that we should be fishing in the pond, which talks about considering reality as a set of processes rather than a set of things. I also believe quantum theory gives us very good reason to believe in a layered reality. As I said, I've half-inched the term implicate order or implicate layer to refer in my terminology, and I hope I'm not doing David Bohm too much of an injustice here. We're talking about similar things. This layer where the amplitudes live underneath our everyday reality, and yet in some sense determine or help to determine what is happening in that reality. We live in a layered universe. And there is something called the Cohen-Specker theorem. Just if you thought it couldn't get any worse, it gets dramatically worse. In the mid to late 60s, this theorem was proven. I can't do the theorem any degree of justice right now, except to point people who are interested in a direction. I've written a little descriptive paper, which I could, descriptive article, which I could make available. But basically what the theorem tells us is this, that if we do ever replace quantum theory by hidden variable theory, then that hidden variable theory must be contextual as well. Trying to explain it very badly, but let's imagine we've got 5 physical properties that we want to measure. Property 1, 2, 3, 4, and 5. And we choose to measure them in groups. So let's say we measure P1, P2, and P3. We set up an experiment to measure those 3. We could have set up an experiment to measure those 3, or we could have set up an experiment to measure those, or we could have set up an experiment to measure those. We got the choice. The Cohen-Specker theorem shows that the property P2 cannot have the same value every single time. What value it will have will depend on the other things that we're going to measure. Try to put it a bit more clearly. Let's say that P2 had a property before we measured it. Then it would have the property, it would have the value when we measured it with those 2. It would have the same value when we measured it with those 2. It would have the same value when we measured. If that is the case, you can't match the predictions of quantum theory. You can't predetermine that this guy will have a particular value whenever you measure it in the different contexts. You've got to let it gain its value, and that gain of value will depend on what context it actually sits in. Prior to the measurement taking place, you cannot uniquely determine the property's value, which is then revealed by the experiment. It depends on what else you're measuring at the same time. It's a pretty complicated theorem to try and explain. I've not done it that well, I'm sure, but again, it's just emphasizing that quantum theory is contextual. Okay, I'm going to draw it to a close. So, I think to try and justify a wholeness to the universe based solely on what quantum theory is telling us, we're on a bit of shaky ground. We're on a bit of shaky ground because I think you could argue that quantum theory is much about discontinuity as it is about continuity and wholeness. Now, again, to be absolutely clear here, this is not me trying to undermine the notion that wholeness is an approach that the wisdom traditions, these experiences that people have, very, very much the opposite. I'm just saying that we try to justify this based on quantum theory. We are on tricky ground, and we need to acknowledge that. I've also projected out some possibilities of where we can say a little bit about what quantum theory tells us about the world. But in all of this, I bow to the absolute master, Eddington. I love this little quote from Eddington. In Einstein's theory of relativity, the observer is a man who sets out on a quest for truth armed with a measuring rod. In quantum theory, he sets out with a sieve. That's a pretty good paraphrase of the distinction between the two. Eddington was a profoundly mystical man, a very, very talented physicist, and he had some very, I think, important things to say. Here's a few. It will perhaps be said that the conclusion to be drawn from these arguments from modern science is that religion first became possible for a reasonable scientific man at about 1927. In other words, what he's saying is some people might conclude that when quantum theory came in, then because of quantum theory, it was possible to be religious. That's what he's saying. 27, quantum theory. If we must consider that tiresome person, the reasonable man, then we may point out that not merely religion, but most of the ordinary aspects of life first became possible for him in that year. In other words, what Eddington is trying to say, if everyone hasn't completely got it, but allow me to paraphrase, because I think this is really important, is that prior to quantum theory, if we were in a Newtonian world, it was very difficult to see how free will and all those other things that we take for granted in everyday life, how they could come about in a Newtonian world. And what Eddington is saying, he's being a bit snarky, well, not being a bit snarky, he's making a very profound point, is that actually, if we'd held to our courage, that we know we have free will, we know we have certain inalienable things about what it is to be a human being, and we didn't see how those fitted into Newtonian physics, so much the worse for Newtonian physics. It was showing us the limits of our physics, not showing us the limits of what we should believe to be true about ourselves. So if quantum theory has loosened the possibility to be religious, then Eddington is saying, hang on, you've forgotten the fact that it's loosened the possibility to be a human being as well. And if you are content to be a human being in Newtonian world, perhaps you should have been content to be religious as well, and just remembered that the physics is only one picture of the world. The bearing of the physical sciences on religion is that the scientist has from time to time assumed the duty of a signal man and set up warnings of danger, not always unwisely. If I interpret the situation rightly, post-quantum theory, the mainline signal, which has been standing at danger, has now been lowered. But nothing is going to happen unless there is an engine. My view is quantum theory allows us to glimpse a scientific description of a world which is nearer to the one that we know we live in. It's not there yet. And I'm not saying it's not an accurate description of things that go on at the quantum level. Of course it is. But I'm saying that it's not yet a complete description of the world. We shouldn't cling to it as a complete description of the world because we know certain things about ourselves. And we should hold those things up against our science, and we should look for consonance between them. And finally, briefly, the position of this. We have learned that the exploration of the external world by the methods of physical science leads not to a concrete reality, but to a shadow world of symbols. I think Eddington here is alluding to my amplitudes, which are descriptions of processes, tendencies to occur. This doesn't sound like a very concrete physical reality. Nonetheless real, but not concrete in the way that we knew it. It does not lead to a concrete reality, but to a shadow world of symbols beneath which those methods are unadapted for penetrating. Feeling that there must be more behind, we return to our starting point in human consciousness, the one center where more might become known. There we find other stirrings, other revelations than those conditioned by the words of symbols. The search of the physical sciences needs to be put against the consonance with our everyday experiences of the world, and perhaps also against those more extreme mystical experiences that happen. And if there isn't consonance, we should hold our nerve and wait for the science, in a sense, to catch up. And what Eddington is saying here is that we need to be very wary of trying to use our science to justify our religious or our mystical convictions. Those come about by other means, and our science may be pointing to those other means, but certainly not justifying them. Thank you very much.
Thank you, Jonathan. Incredible, incredible presentation. Would you be able to close your screen share for a moment, just so we can open up the screen so that we can see everybody? Thank you so much. Well, we have very little time left, but if somebody would like to come in and ask a question, this is the moment to do so. You can use your raise your hand function that you can find under reaction at the bottom of your screen.
Who wants to disagree with me completely?
That's risky. I see a lot of hands clapping and gratitude for what you've shared with us today, Jonathan. Sperry, would you like to come in and ask your question?
Yes, thank you, Eleanor. Jonathan, in the film Infinite Potential, we see that the Bohm's work can show what appears to be the particle paths changing dependent upon on the observation. You familiar with that computerized graph of his later work?
Yeah.
Where the particle path was able to be deterministically shown, perhaps statistically, but in any case, could you comment on that, please?
Well, going back to what I've said, Bowman-Hiley's approach certainly deserves a great deal more scrutiny than it's actually gotten, a great deal more discussion in the community. And one of the things I'm quite excited about with my meeting with Basil, which is going to take place in a couple of weeks' time, is that there's certainly been experiments which are called soft measurements, where you kind of brush up against the particle a little bit, and they've used those to track out the particle trajectories. But to be fair, they're still not measuring the trajectory, because what they're doing is averaging over lots and lots of different particles, and they do reproduce the trajectories, as would be predicted by the quantum potentials approach. In fact, I showed a picture on one of my earlier slides, which was the drawings of all those different, and so they do appear to be, these soft measurements do appear to be reproducing those. The problem, though, is that that's not actually telling us the individual trajectory of one particle. You can only get those soft measurements as a result of measuring loads and loads and loads of particles and kind of averaging out over them. But it is also true to say that, in a sense, if you take an observation, if you make a measurement, then you're going to constrain the possibilities and narrow down the field of possibilities, and that's going to narrow down the trajectories that take place as a result of changing the experimental apparatus or making your measurement. And again, in the context of Basil and Bohm's approach, this whole thing about state collapse just doesn't actually happen. What the wave function does is it determines the quantum potential, and this quantum potential is a strange new form of energy which doesn't, in a sense, force the particle along the trajectories. It kind of guides them, a bit like railroad tracks. And if what we used to think of as state collapse would be, one possibility is manifest rather than others, what they're saying is that they're all there, all the different trajectories are all there. It's just the electron gets shunted onto one rail or another, depending on how it quite first started. So there is no need for state collapse in that sense. So it very much is worthy of consideration. But again, my worry is that if there is no one interpretation, and we'd include Bowman-Hiley as that, if there is no one interpretation that shouts at us as being definitively correct, that might be a signal that we still haven't quite got our concepts right, that there might be some replacement theory to which Bowman-Hiley's might be an approximate truth. But when we get to that theory, we shouldn't be arguing about the interpretation. The theory should be telling us what its own interpretation is, I feel.
May I ask you, the Aharonov-Bohm effect, does that add any greater clarity about what might be influencing the particles to take?
I don't think it adds anything in that regard, but it does make the quantum world distinctly more mysterious. For anyone that's not familiar with what this Bowman-Aharonov effect is they showed that if you have a very localized magnetic field, imagine that this thing is a coil of wire, and we run a current through it. It doesn't look very much like a coil of wire, but I want you to imagine this is a cylinder of wire. We run a current through it. Then there's a magnetic field concentrated down the center of it. And there's very little magnetic field around the outside. And what they showed was if you had a double slit experiment and you put this magnetic field here, so close to the slits that any electron that went through that slit, wouldn't pass through the magnetic field. Nevertheless, when you switch the current on, it did alter the interference pattern. So that even though the particles, in a sense, their trajectories weren't taking them through where the field was, in some sense, they were aware that the field was there, and that influenced the interference as a whole. Now, that can be completely explained within the context of quantum theory. It's not something that's deeply mysterious in that sense. Mathematically, it's completely explainable, but it's another very singular experimental indication that the quantum world is a very, very funny place.
Thank you.
John.
Thanks, Barry, for coming in. Can we take one more question? How do you feel about that, Jonathan?
Yeah. I'm the one that's yattered on. I should give other people a chance.
Raymond, please come in.
Thank you so much for such an enlightening talk. You focus upon, in your explanation of the quantum experiments, two variables chiefly, the particle which is being measured and then the measuring device.
Yeah.
But not particularly the consciousness of the observer who was designing both the device and the experiment. So I guess my comment is, isn't what happens, this idea of what interaction changes reality, isn't what happens when you measure quantum interactions, is that you're changing the reality of the observer, which means you're learning something. And that's where the change, that's what I'm seeing as what changes.
Yeah, no, I would go along with that. The reality is changing as a result of measurement, but again, you know, reality is a very loaded word. You know, I think there are two realities at work, or two aspects of reality at work, or two layers of reality at work. You know, we've got the layer at which these things, you know, we live in, and the implicate layer underneath, which is where the business of the amplitudes go on. And somehow or other, that business underneath is governing what's going on up here. And that when we make a measurement, the amplitudes kind of get together and say, well, what are we going to do? We're going to go for this one. I'm going to go to that. And then suddenly this particular thing pops up in our world. And that clearly informs us, and it changes the nature of the world in some way that we don't understand. There are many options on the table as to how this actually comes about. But I think, again, my point isn't so much that this doesn't change the world. It isn't so much that that what goes on at our layer isn't informed and influenced by the implicate layer. It's just seeking wholeness in that regime is possibly not, you're not going to find it, because what we're actually seeing is a very discontinuous, sharp change that comes about. Now, it may be that in some future theory, perhaps Penrose's, you know, theory where gravity comes into it, then our description in terms of a sharp change will get modified. And what we see as a sharp change will actually turn out to be a gradual change, a gradual evolution that happens over very, very tiny scales of time. And so maybe in which case my objection will vanish, because then there will become a bit more whole. But as it stands right now, the measurement process, the measurement problem is about a sharp, discontinuous change. And many of the solutions to it, mind causing collapse, some complex measurement device causing collapse, whatever, effectively draw a line across the world, subdivide the world into two bits. And again, that's for me is not wholeness.
And if I understood the end of your talk, I took it in a very hopeful way that we kind of need more than science. So it made me think, isn't mathematics itself a machine, a measuring device?
Well, yeah, no, that's a very interesting point, because certainly I very much mentioned in passing that Penrose thinks about in terms of non-computational things going on. Penrose is very big on the algorithms and computational physics, and makes in my view, quite a strong argument to do with AI, about non-computation. And so he's postulating that maybe calculational, algorithmic, grind out the numbers type physics is in the end going to fail us, and that we need a more geometrical approach. I don't know if you've seen, a Mobius strip. What do you know what I mean by Mobius strip? You continuously, everybody has one side. Now, he's saying that if you just look at one tiny piece of a Mobius strip, you would think it was two sides. You only get the properties of it by considering the whole. There's that word. And he's saying geometry can express wholeness in a non-computational way. And it can express contextuality in a non-computational way. And so therefore he's saying that maybe this is a glimpse of what the way physics needs to go to explain or incorporate mind and everything else. And I think I'd modify your point slightly by saying that, yes, mathematics is a machine, it's a tool. Maybe what we need is a slightly different form of mathematics, a non-computational form of mathematics, which would still be a form of mathematics. Did any of that make sense?
Oh, absolutely. Thank you so much.
Thank you, Raymond. Well, we have gone a little over time. I'd just like to thank you, Jonathan, first for putting together this incredible program, and then for your brilliant presentation today, which I think you will see from the chat has been appreciated by so many people. So thank you so much for today. And thank you everyone for being here and making this program possible, because without all of you, we wouldn't be here today. So thank you. And we look forward to seeing you tomorrow when we will be talking about global consciousness, manifesting meaningful structure in random data with Dr. Roger Nelson. So we look forward to seeing you tomorrow. Please note the time change, because we've already changed here in Europe. For people in the US, obviously it will be an hour earlier tomorrow, the session. So that'll be 9 o'clock Pacific Standard Time, 12 o'clock Eastern Standard Time. And then in the UK, we stay at 5 o'clock. And in Italy, in Central Europe, we will be at 6 o'clock. So we look forward to seeing you tomorrow. Thank you all for being here.
Sorry, Helen, just very, very quickly before
Please.
you hang up. Can we, I'm keen to allow, I'm keen that people should follow up, if they want to ask me a question, follow up with this conversation. Can we use Sutra or something like that?
Yes, actually, yeah. And there was actually something that I was going to bring up with you, that it would be nice if, not necessarily with you, but I was going to give a space to the participants midweek where we will open up a session for an hour where participants can just talk about what has happened during the weekend sessions and have a space just to talk amongst themselves. So
well, if
I will let everybody know tomorrow when that will be.
I will happily join in.
That would be amazing. So we will coordinate together, Jonathan, when that would be a good time. But yes, we would like that for these 3 weeks, midweek, there will always be an hour session for people. That is just for you participants to talk amongst yourselves. Anyways, we will let you know. And yes, Sutra. Okay. Thank you, everybody. Have a great rest of your day. And we will see you tomorrow here at the Bari Center. Bye-bye. And thank you, Jonathan.